structures for these three. See what you get. It's the one, it's a whole big page full of boxes.
Is there anyone else that was here for the SI session that didn't sign in?
After Rule 6.
Well, it's good until you have like 30 sheets. Because you got the check-ins, and then you got the tracking ins, and then you have the time sheets. So it just keeps it all electronic. She gets a nice big zip file. The week on Tuesday, automatically send it to her phone. And it's in Excel, so it auto sums it right there at the times, it signs them out. Yeah. Okay. Thanks, guys.
Thank you.
what's on the board right now is wrong. Or maybe I shouldn't say wrong, it's incomplete. That is what you would have for each of these structures at the end of Rule 4. Where you've gone through your counting electrons, you've apportioned them out as far as bonding and not bonding. What's on the board right now is as far as that formula is going to take you, as close as it will get you toward the actual finished structure. Is there any question getting to that point before we start doing the visual stuff? The folding in, the resonance, the exceeding octets, those sort of things. If there's any question getting these to this point, please ask. All right, what would you do to finish off the SO2-Cl2? Resonance?
Knock that out. Because the other oxygen wants another one too.
It does, but what's the maximum for sulfur? It wants 8, and what's the maximum that it can be forced to have? Did we do Rule 6 before?
No.
We didn't. Where did we stop?
We stopped.
5. We stopped at 5.
Oh, no wonder. Sorry about that. Rule number 6. You've got this little grid-looking thing at Rule 6. Grid-looking thing meaning periodic table. And it corresponds to these elements. So write these into the little squares that you've got here. Back the way it was for the moment. There are some elements, rule number 6, there are some elements that can be forced to exceed the octet. They want to have 8, but they can be forced to go beyond 8. This is them. And the reason why is that these are all nonmetals that have d orbitals. They've got empty d orbitals, but that's where electrons can be forced in. When we talk about valence, we're talking about S and P. And if you're only one energy level big, all you've got is S. 2 would be the maximum. If you're 2 energy levels thick, then you've got S and P, and that 8 would be the absolute maximum. Not just what's preferred, but the absolute maximum, because there's no such thing as 2D, correct? But when you get to level 3, you've got S, you've got P, and you've got D, and even though for these, that set of d orbitals is empty, they're still there and they're still available for bonding. And so things that are 3 for nonmetals, 3 energy levels thick or bigger, meaning these, they can be forced to go beyond 8. And the pattern is this as far as maximums. Phosphorus and arsenic can go as far as 10, sulfur, selenium, tellurium to 12, the chlorine column to 14, and argon column to 16. As far as what they want, as you count across the S and P blocks, it went 2, 4, 6, 8, 8, 8, 8, 8, correct? But as far as what the maximum is, it doesn't plateau at 8. It keeps on counting. It's 2, 4, 6, 8, 10, 12, 14, 16. But that doesn't apply to nitrogen, oxygen, fluorine, neon, because those don't have d orbitals. 8 is their absolute maximum. But for these that we've got written on the board there, for those particular elements, they can be forced to go beyond 8. What is sulfur's maximum? 12. So the way that this is drawn right now, the sulfur has 8, which is what it prefers. But the problem with the structure is oxygen not having a second bond. And so this oxygen will fold in to form a new bond. That puts sulfur at 10. This other oxygen will fold in a pair. That puts sulfur at 12. And that would be your finished structure. Every atom fits with what we've discussed. Not necessarily with what is preferred. But the new thing about Rule 6 is these maximums. And the key word was, when I defined that a minute ago, was can be forced to exceed. How many valence electrons does sulfur want? 8. How many bonds does sulfur want? 2. But it doesn't have that in this case. It's forced to go all the way to 12, primarily because of these oxygens. Oxygens are high electronegativity, they drive the process. The oxygen will get the bonds that it wants, and that forces sulfur to go beyond 8. Question about that. So then compare that to phosphate. Are any of those oxygens where they want to be, according to the drawing? No. They want to be in a situation where they have 2 bonds. So comparing this to the chart over there, will this happen? Yes. Will this happen? Not without flipping the other back out, right? That's kind of a trick question, because if the question is, will oxygen fold in a pair to get a second bond, then the answer is always yes. The question is, what happens as a result? This would overload phosphorus, right? 1, 2, 3, 4, 5, 6 bonds. 6 bonds did not overload sulfur, but it will overload phosphorus. And so when that one kicks in, this one's bumped out, now you got resonance. That one has resonance. And you would draw it as if 3 oxygens were single bonded and 1 was double bonded. Adding the word resonance indicates you really don't believe it's 3 single bonds and a double bond. That extra bond is kind of oscillating through. It's distributed, and despite how it looks, that is equal bonding to all 4 oxygens. Question about that? Know that little chart of maximums. And then this one, nitrogen will fold in a couple of pairs, and this would be your finished structure. Boron's octet is just 6. Go ahead.
Would you mind explaining the 6th rule again?
As far as what the pattern is, or why the pattern is what it is. The pattern, if we go back to that chart that we had, and as far as the octets, the amount they want to have, it was 2, 4, 6, 8, and it stayed 8. And as far as what their absolute maximum would be, for these elements, it's still that. But it's not, it's when you start getting into these and the ones that go below them, then it doesn't plateau at 8 anymore. because now you're dealing with elements that have d orbitals. So they have the equipment to store extra electrons. And other elements, especially oxygen, will take advantage of that. There's a means of obtaining its second bond. Go ahead.
Will you explain why the importance of putting resonance on that one is?
Because when you look at it without that, it looks like one of those oxygens is double bonded and the other three aren't. And it's not really like that. Experimentally, all 4 bonds to oxygen are equal energy. And the energy of those is somewhere in between what would be the energy of a single bond and what would be the energy of a double bond. Okay, just making up numbers for a second. If a single bond had an energy value of 100 kilojoules, but a double bond had an energy of, say, 200 kilojoules, then this is not a 200 kilojoule bond and these others are 100 kilojoules. Experimentally, they're all about 120, okay? Meaning that energy is averaged out amongst them and they all have equal strength, okay? And so the reason they have equal strength is this bond here that we've got drawn in on this one oxygen is really here and 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 here. And so the resonance word is saying, you know, that's distributed.
I thought that oxygen is strong, it always gets what it wants. Like if it wants
Yes,
to
and resonance is how each of those oxygens taps into a second bond.
Like it's covalent?
For covalent?
Is that because it's covalent? It's always sharing?
Because it has to share, yes. That's right. Other questions? All right. Now the thing about this one, despite how the symbols are written, what you've really got here is a sulfur with 4 oxygens on it, and these 2 hydrogens are not on the sulfur. They're not connected to the sulfur at all. You've got, basically, this is a sulfate ion, sulfur with 4 oxygens, and 2 of those oxygens have a hydrogen on them. Those hydrogens are out on the perimeter. So, there are no H to S bonds in this. So we go through our little tabulation. Each hydrogen contributes 1, sulfur is 6, each oxygen is 6. That's 32. Connecting up the atoms is going to be 2, 4, 6, 8, 10, 12. Because we have to connect those hydrogens onto the oxygen. So 32 to place, 12 of them are bonding. That means there's 20 more to go that are not bonding. We start putting those in with our high electronegativity atoms, 20 of them. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And that would be your structure at the end of rule 4. Will this oxygen fold in a pair to get a second bond?
Yes.
Yes. What does that do to sulfur? Puts it at 10 electrons, which is okay for sulfur. Will this one fold in a pair to get a second bond?
Yes.
What does that do to sulfur? Puts it at the maximum, which is 12. Will this oxygen fold in a pair to get a third bond? No, because it's already got 2 bonds, right? It's not that oxygen necessarily wants a double bond, it wants 2 bonds, and 1 to sulfur, 1 to hydrogen is fine. There's no resonance in this one. Because every oxygen, the way it's drawn now, every oxygen has 2 bonds. These get it via double bond. These get it by 1 to sulfur, 1 to hydrogen. But that would be your finished structure, and there is no resonance group.
So it's all that hydrogen always connects to oxygen.
If you're dealing with one of these polyatomic ions, then yes. You can't say that it's always going to be attached to oxygen. A lot of times it will. But especially if you see something that's like an acid, like phosphoric acid or sulfuric acid, then yeah. Because that phosphate or sulfate, that's a polyatomic ion with hydrogens on the perimeter. There will be an ion in there that you should recognize. Maybe you don't necessarily recall the name of it, but you should recognize that as a polyatomic ion. And then you put the hydrogens on the perimeter. Are they okay with this not having resonance? All right. Draw sulfate. It's not one of the squares you've got, but since it's related to sulfuric and we've been talking about sulfuric, just do it in the margin there. Is that what you got?
Why'd you put the second double bond? Didn't you just put the first double bond and set it right?
No, because you will have 2 double bonds in that, because sulfur has a maximum of 12.
Oh.
And so the oxygens will push the sulfur as far as they can.
For the test, do we need to memorize that?
That little chart over there?
Yes, this chart and another one.
Yes. of is very visual pattern based as far as how that chart works. And so if you memorize the patterns to it, it won't be so bad. So looking at that sulfate structure, how many oxygens at any given moment are looking for a second bond? Two. So is it any surprise that when hydrogen becomes available, this forms a 2-hydrogen acid? Is this one going to grab a hydrogen?
No.
No, because it's perfectly fine the way it is, right? When you have that structure for sulfate, 2 of them at any given moment, 2 of them are going to be okay the way they are. They're perfectly content with their double bond. It's 2 that are still seeking an extra bond. And so it's going to be a 2-hydrogen acid. You see how that's related? You see that this does not have resonance, but sulfate does. All right. Good. Okay. So next then is taking what we've done with Lewis structures and using that to dig out other structural information. This is all based on what's called Vesper theory. And what you've got listed here under the heading Vesper theory are 9 different structural characteristics that you ought to be able to look at a Lewis structure and figure out. And what we're going to do is go through each one of these and make comparisons. It's all based on valence shell electron pair repulsion theory, which is a very complicated term for principles you already know. First of all, when we're doing Lewis structures, you already know we're only dealing with valence shell, right? Core stuff we ignore. All that chart we had was valence shell stuff. All the electrons in the Lewis structure were paired. They were either in a bond, counting as a pair, or they were a lone pair. But all the electrons were paired up. And electrons, all the negative, they give you repulsion. So all that theory says is the electrons that you've got and the valence levels repel away from each other geometrically to design the shape of the molecule. So we're going to look at the shapes of the molecules and other factors related to that as we go through. I'm sorry?
Could you please repeat that? What did you just say?
This? No, because it's irrelevant, really. I mean, that was just saying where the name of this theory comes from, and who cares where the name really comes from, okay? That's, that was more toward the idea of don't let the name bother you, okay? It's a more technical theory than it needs to be, okay? So file that under trivia and or irrelevant. Now, how to apply these things is important. And so to start this with, a couple more pages back, you've got some more boxes for Lewis structures. And what I'm going to do is put a bunch of these up here on the board. And you can copy them into the little squares here. But when you do that, copy them in small. Because what we're going to do is have a structure in there, and then we're going to go through and talk about all these properties, and you'll be writing a lot of information in there too. So save a lot of room for writing the information about these structures. Make sure you get all the dots copied.
Did you skip the setting and recording one?
Yeah, I'm not putting them all up there.